All right, so at the start of 4.4, I want you guys to think back to something we did actually in chapter 1 when we talked about real numbers. And as far as we knew at that point, I had told you that every number ever that you had counted was a real number. And so we brings to today's lesson where we're talking about something called imaginary numbers. And so that's kind of the counter to what a real number is called an imaginary number. So another rule that you guys have been taught over the years is that you can't take the square root of a negative number. So imaginary numbers kind of break that. So here's the way that the imaginary number is defined. We've got kind of two definitions for it. So we literally just use like this cursive I for imaginary, and we define it to be the square root of -1, which, like I said, is something that hadn't been defined before. And so we also will sometimes say, if we square both sides, we'll define I squared to be equal to -1. So these are two things that have never been allowed to happen with the rules that we've got. We've never been allowed to square root a negative, and we've also never been able to square a number and come up with a negative. You've always been taught that if you square something, you get a positive. So this is the definition of the pure imaginary number. It's defined as the square root of -1. So pure imaginary numbers are numbers that are some sort of multiple of I, which is this imaginary number. So in these first two examples, we're going to simplify up square roots. So normally you can kind of break these down into what's prime and what's not prime, or I'm sorry, what's perfect square and what's not a perfect square. So first thing I want you guys to do is I want you to separate this to the square root of -1 times the square root of 28. Anytime you've got a negative under, split it up like this. You've got a property that says you could re-multiply them if you wanted to, but this is going to help us simplify. And then 28 itself is not a perfect square, so we want to break that down even further. So keep the square root of -1, and then 28, we can write that as 4 times 7. So 4 is a perfect square, 7 is not. So square root of 4 times square root of 7. So we're going to simplify each piece down. So square root of -1, we defined right up here to be I. So that's going to be part of our answer. Square root of 4 is just 2. And then square root of 7 is just irrational. We can't simplify it. We just leave it like that. So the way that we will write these out, you will always see a normal, like rational number first. Then you'll see the imaginary number followed by any sort of irrational number. So that's how you'd write your final answer there. That's as simplified as that square root can get. All right, so let's do another one. Same split. Write the -1 first times the square root of 32, and then 32 itself, not a perfect square, but you can break it down into a perfect square. So 32 you can break down to 16 times 2. So if we multiplied all three of these numbers together, we would come back to the -32, but we're trying to split it up so we can simplify. So again, square root of -1 is defined as I. Square root of 16 we know comes out to be 4, and then square root of 2 is still irrational, so we just leave it under the square root. So again, same as before, you always write the rational number first, then the imaginary number, and then the irrational number after that. So that would be your simplified version of root -32. Okay, so that's some ways that you can simplify using that imaginary number. One little thing we want to write down is powers of I. Like here's I, and then we have I squared, which means we can kind of build off itself and keep multiplying and keep adding powers. Okay, so here we go. Here are the first handful of powers of I. So I to the first, of course, anything raised to the first power is just itself. I squared, we already defined. I squared is -1. I cubed, what we can do, any sort of powers, because remember, this is I times I times I. So we can break it up and say that it's I squared times I to the first. And so remember, I squared is just -1. So this would be -1 times I, which is -I. I to the fourth, we're going to do the same sort of split that we can do here. And this time we're going to break it up to I squared times I squared. So I squared, they're both -1. So we've got -1 times -1, which is +1. Sorry, I'm kind of sneaking that in there. So this is a little strange. When we take an imaginary number and raise it to the 4th power, we just end up with like a nice normal 1. Okay, so let's keep going. We'll do another row. So I to the 5th. So we love I to the 4th. We're going to keep using I to the 4th. So anytime we can, split it up into some version of I to the 4th. So this will be I to the fourth times I. So I to the fourth is just 1, and 1 times I is just I. So I to the fifth is actually just equal to I. Now let's look at I to the sixth. So remember, like I said up here, we love I to the fourth. So 6 powers, we can split it into 4 powers and 2 powers. So I to the fourth is 1. I to the second is -1. So this is equal to -1. Okay, we're going to do 2 more. We'll do I to the seventh. Again, we like the 4, so we're going to split 7 into 4 and 3. I to the fourth is just 1, and then I cubed is equal to -I. So hopefully you're seeing this pattern here. I to the first, I to the fifth are the same. I to the second, I to the sixth are the same. So are these two, which I'm sure you can guess that I to the eighth would end up being the same as I to the fourth. We can split this into I to the fourth times I to the fourth, which we could write even more compactly as I to the fourth squared. So that's just the same as 1 squared, which is 1. So this cycle is just going to keep repeating itself over and over and over. So in the same spots, you'd have I to the 9th, 10th, 11th, 12th, I to the 13th, 14th, 15th, 16th. It would just cycle over and over and over again. And the pattern goes like this. I, -1, -I, 1. I, -1, -I, 1. And it would keep cycling over and over again. It has a cycle length of 4. So every 4 powers, it repeats the cycle. So we're going to use that later. This example, let's simplify some of these up. So when you're multiplying, same as you would do with variables, we multiply the constants together first. So the -3 times +2 gives us -6. And then we'll multiply I times I, and we get I squared. You should never, ever, ever leave powers of I in a final answer. It's not simplified if you still have powers of I in a final answer. So we reference what we've got up above, and we know that I squared is actually just the same as -1. So we're going to replace the -1, and -6 times -1 comes out to be a +6. Okay, so it starts to get sort of crazy when you notice that we multiplied 2 imaginary numbers together and came up with just a normal 6. Okay, so we can do the same sort of thing here. Let's split these up. So -√12, I know that I can pull an I out front by doing the same thing as this. And then √12, let's see how that simplifies, times, and then I can do the same thing with this. I can bring an I out front, and then this is √2. Okay, so we can clean this up a little bit. So 12 is 4 times 3. All right, so we can take out the square root of 4. Square root of 4 is a perfect square, so we can bring it out as 2. So we've got 2I √3, and then times I √2. All right, so let's start to multiply all these things together. So the 2 doesn't multiply by anything else because there's nothing else that's rational. So we've just got that. I multiplies times I, and we have I squared. And then √3 multiplies by √2, and we have √6. Okay, so just to keep cleaning this up a little bit, remember we're never going to leave powers of I in our answer, so we can go off the fact that I squared is equal to -1. And one more simplification, we'll just write that as -2, and then times the square root of 6. So that would be your final answer for that one. Okay, so let's look, we got a little bit more in this video right here. So I to the 42nd, so this is what I was talking about, we'd be using those powers of I. So if you go back to our cycle here, it repeats every 4. So basically what you want to try to find is when was the last time that it hit a power of 4. So here's how we're going to write this. 42 is not a multiple of 4. The last multiple of 4 would be 40, so we can start to break it up like this. We're going to write it as I to the 40th times I squared. And again, the reason we choose the 40th is because this is a multiple of 4. So we want to find a multiple of 4 because I to the 4th comes out to be 1. So we want to be able to work with that. Then we're going to split it up and write this as I to the 4th raised to the 10th power. So like I to the 40th would be I to the 4th times I to the 4th times I to the 4th 10 times. That's how you get your 40 total copies. And then times I squared. So now we can start subbing in some of the values that we have on that chart on the previous page. So I to the 4th is just 1. And we raise that to the 10th. And then I to the 2nd would be -1. So 1 to the 10th is just 1. And then times -1 would be -1. All right, one more. So for this, we're going to bring in something called the square root property. It's similar to the idea of difference of squares, except now we're factoring it over imaginary numbers. So what we do works like this. We start by subtracting this number over to the other side. We're basically trying to get our variable by itself because this doesn't factor. So we've got to work for an alternate method. So we subtract 20. So we have 5y squared equals negative 20. The next step would be to divide by this 5. So these will cancel. So at this point we've got y squared equals negative 4. So we know under like normal rules that we've had up until this point, a squared number can't be equal to negative 4. But all rules are kind of out the window when we talk about imaginary numbers. So we take the square root. So we get y equals, so if you remember, we have this idea when you take the square root when you're solving equations that taking a square root you could have a positive or negative version because technically square roots could come out to be, again, the negative version or the positive version. And then the square root of 4, we know the square root of positive 4 is 2, which would make the square root of negative 4 2 times I. So it would be an imaginary number. So we've got two possible solutions to that equation. Okay, so we introduced the imaginary number. The pure imaginary numbers are just like basically a number attached to I. Complex numbers kind of expand that a little bit. A complex number is anything of the form A plus B I. So A and B would just be numbers, so for example, you could have like 2 plus 3i. That would be an example of a complex number. Technically, you could have like just a 7i, because in that case, the a would be 0, which means you could also have like just a negative 5, because in that case, b would be 0. So it can be the whole thing, or either a or b could be 0, so you could have just imaginary or just like a normal real number. So any of those would be technically complex numbers. Just like when you're dealing with variables, these are not like terms, which means they can't be combined any farther than that. So again, this expression is known as a complex number. So we're going to be doing operations. We're going to be adding, subtracting, multiplying, and dividing complex numbers. Okay, so